Hello everybody! Thank you for joining me today as we learn about dispersion and rainbows. To kick this video off, we'll begin with a brief overview of the basics of light. We know that light travels as a wave and therefore has a wavelength and a frequency. These wavelengths correspond to different types of light. Our eyes can only perceive a very small portion of light. This is called the visible light spectrum. Visible light is red through violet, with red having the longest wavelength of approximately 700 nanometers and violet having the shortest of approximately 400 nanometers. White light is a mixture of all visible wavelengths of light. Sunlight is technically white light, although it appears slightly yellow because it doesn't have a perfectly even mixture of the wavelengths of visible light. With that out of the way, let's jump into our topic for today, dispersion. Dispersion is where white light spreads out or disperses into its full spectrum of wavelengths. The wavelengths separate and the colors become distinct, and a rainbow is formed. So what causes dispersion? Dispersion occurs when there is a process that changes the direction of light in a manner that depends on wavelength. Refraction is one such process, and it is the main reason for dispersion in rainbows. Rainbows are formed by a combination of refraction and reflection. When light enters a droplet of water, it is initially refracted and disperses into its different wavelengths. Because refraction is dependent on both the medium and the wavelength of light, the different colors have different angles of refraction due to their differing wavelengths. Red light bends the least, and violet light bends the most. This is why the light separates instead of all changing direction uniformly. After this initial refraction, the light rays hit the back of the raindrop and are reflected. This is called total internal reflection, because none of the light leaves the raindrop at this point. Because reflection is not dependent on wavelength, this step does not contribute to dispersion. The light rays then exit the raindrop and are refracted a second time, now with even greater separation of color. Because of this dispersion, only a small portion of the light traveling from an individual raindrop reaches our eyes. We see the full rainbow because of the light coming from many, many raindrops. The waves travel to our eyes from the raindrops, and we see the rainbow with red on top and violet on the bottom. Taking a step back, why does the light reflect off the back of the raindrop instead of simply being refracted again? It all has to do with the angle at which the light hits the back of the raindrop. To produce total internal reflection, the incident angle must be bigger than the critical angle. The critical angle is the incident angle that would produce an angle of refraction of 90 degrees. So, what is the critical angle for light going from water to air? If we look at Snell's law of refraction, we see that we need the indices of refraction for both water and air. Because we're already inside the raindrop, N1 will be 1.331, or the index of refraction for red light going through water, and N2 will be 1 for air. We can plug in 90 degrees for theta 2, then solve for theta 1. You may pause the video now to go through the calculations yourself, then we'll go through them together. Alright, we can start by plugging in our known values. Since the sine of 90 degrees is just 1, we end up with this, which gives us a critical angle of 48.7 degrees. This means that the angle of the red light after the initial refraction needs to be greater than 48.7 degrees, or total internal reflection will not occur. From there, we can calculate what the incident angle of the sunlight hitting the raindrop needs to be, again using Snell's law. Since we're starting in air and moving into water, N1 is 1, and N2 is 1.331. We're using the index of refraction for red light again because we found the critical angle for red light in the previous example. We can plug that in for theta 2 and solve for theta 1. You may pause the video now to go through the calculations yourself, then we'll go through them together. Okay, we can plug in our known values, and then we can rearrange our equation to solve for theta, which gives us incident angles of about 89.3 degrees and 90.7 degrees. This means that the sunlight must hit the raindrop at an angle between 89.3 degrees and 90.7 degrees to produce a rainbow, which is a pretty narrow window. Rainbows are so cool. So what about the incredible double rainbow? The sunlight that produces the second rainbow hits the raindrop at a different angle from the first, which allows it to be reflected twice before it leaves the raindrop. This second reflection inverts the rainbow, and so we see the second rainbow with violet at the top and red at the bottom. This secondary rainbow lies above the primary rainbow, is twice as wide as the first, and is fainter due to the extra reflection. To wrap up, here's a short recap. Dispersion is when white light separates into its full spectrum of wavelengths. This is caused by refraction. Rainbows form because of this process of refraction, as well as total internal reflection inside the raindrop. The light reaches our eyes, and we are blessed to see a beautiful rainbow. Thanks for listening. Enjoy God's magnificent creations, including rainbows.